All right, welcome to week 3, descriptive statistics. This week, the big topics are measures of center and spread. The big measure of spread this week is mean, which I'm sure you're all familiar with. It's also called average or arithmetic average. And it's just the sum of the values divided with a count, how many values there are. So that'd be like the sum of the frequencies, sum of the values over the sum of the frequencies. And it's a measure of center, but there are other measures of center, for example, median, and the mean and the median don't necessarily agree. That means they're not the same number. Now, spread of the data is important too, and the big idea this week for spread is standard deviation. And last week we had min and max, and those give us the range. Then we have quartiles, and the distance between the first and third quartile, that's the interquartile range. So those are all measures of spread. But standard deviation is probably a bit more important. It's definitely a bit more important. So it's a measure of average spread from the center. Okay. So again, it's average spread of the data from the mean. So you cannot talk about standard deviation, this average deviation, without the mean. And so I want to look at a few graphics and explain that a little bit. As far as formulas for that, we just need the spreadsheet formula for it, which is stdev.s for sample. There's a slightly different calculation for populations, which we almost never have. And then whatever your data is goes in here. Okay, so that would be your data set from the spreadsheet. And you definitely should read the book, and the book goes over how to calculate it by hand, but we will never do that. So let's take a look at a spreadsheet. So I asked you in the beginning of the quarter about how much TV, video stuff you watch on average each day. And oops, sorry about that. I have a little more than just you all. So here's the summer 2020. I threw my spring students in here too, just to get a slightly bigger data set. And for the summer people, I have gender. I'll add that later for the spring people. I was kind of curious if there was a difference between male and female based on this very non-random sample. And again, this is a non-random sample. So I have some summary statistics here. Let's blow that up a touch. Count how many numbers are there, the average, which is the mean, standard deviation. Notice I'm using the .s version. That's the same thing as stdev, which a lot of spreadsheets have also. So for example, if I want to calculate the average spread of this data, equals std, if I could spell, and there's a few you do want to choose, there's a few you don't. So my recommendation is just the plain stdev or the .s for sample, and those two do the same thing. So select all the data, close your parentheses, hit enter, and out pops that number right there, which I chose here to round to 3 decimal places. The rounding rule in statistics, please recall, is to go 1 more decimal place than the data, and at first it looks like my data might be to the nearest 10th, but there is at least one number that has 2 decimal places. So then I should, if I need to round, to 3 decimal places. So then we have the min, Q1, median, Q3, and the max. So I could use this 5-number summary to draw a box plot or use a box plot generator. And that would give me some idea about how spread out the data is. When we talk about the distribution of values in a data set, that's kind of like how are they clumped together, how are they spread out? And generally, we like to look at that visually. So here's a histogram, let's zoom out a sec, that shows that. And I group these in a very specific way. Notice that these are not nice numbers down here. And if you look at my frequency table here, you can see that my max hours have some strange numbers here. So why did I choose these particular numbers? When we work with a standard deviation, and remember, standard deviation is a measure of spread from the mean. The mean is a very important number, so I'm going to highlight this right here. My mean is 3.152 is what I'm using here. Let's see, yep, that's what it was here. So what I'm doing is I'm using the mean as one of my max values in my groups, and then from there what I did is I subtract the standard deviation one at a time going that way, and I keep adding the standard deviation going that way. So the width of each of these ranges here is the standard deviation. So when I graph this, and I have a slightly better graph below here, the width of each interval here I made for my groupings is the standard deviation. So each of these is about, to 2 decimal places, 2.16. And again, Google wouldn't let me graph down here with 3 decimal places, so I had to go with 2. So here is my mean right here, and then this is 1 standard deviation to the right, 2 standard deviations to the right, 3 standard deviations to the right, and 4 standard deviations to the right. So I'll draw that out in a picture in just a moment. So I have it just displayed a couple of different ways. So a lot of times you'll see graphs like this in the media. Sometimes we'll be more specific and state what's the starting number and ending number for this group right here. Okay. All right. So frequency table. This is a frequency histogram, and this is just another frequency histogram with wider columns, but it's the same chart as that one right there. I just have a slightly different scale. All right, let's check out my notebook so we can draw on this. All right, so here we are again with that second frequency histogram. And let's see, this right here is what we call X with a bar over it, and that's the mean. So the mean is kind of the center of our distribution. And this distribution right here, it's kind of almost symmetric in this hump right here, right? There's almost a symmetric hump there. If I shift it a little bit, my starting and ending points for these boundaries, it would look more symmetric probably, but it definitely has a right tail. And so if we did a few different histograms on this, we'd probably see a right tail all the time. So one thing I'd note about this, because this has a right tail, this distribution, and again, distribution just means the shape of the histogram, how the data is spread out, how it's clumped together. Because this is a right tail, we say it's skewed right. The skew is to the tail. This is important. So skewed right. So it's got a slightly symmetric bell, but a right tail, so it's skewed right. Anyway, then the distance from here over to there is 1 standard deviation. So usually we use the letter S for a standard deviation. And then the distance from here to here, that would be another 1S. So altogether, to get to this number right here, I started at the mean and then I jumped 2 standard deviations. So that value is X bar plus 2S. And this number right here is an upper bound for outliers. Now similar on the other side, I can go back that way, so I could subtract 1 standard deviation, and then I could do that again, subtract another standard deviation. And so this number right here would be the mean minus 2 standard deviations. And we can calculate that in the spreadsheet to confirm it. And so this would be a lower bound for outliers. And when we count by standard deviations, that count is called a z-score. And again, what is a standard deviation? A standard deviation is a measure of average spread from the mean. You can't leave out that from the mean part. Okay? It has to originate from the mean, and we see how far things are out from the mean, and we kind of average all those distances to the right or the left. So as far as z-scores go, if I draw those in red, the mean would have a z-score of 0. This would be 1 standard deviation to the right, 2, 3, and 4 standard deviations to the right. Going the other way, to the left, would be -1 and then -2. So notice there are no data values more than 2 standard deviations to the left, because then we get into negative numbers and you can't watch a negative amount of TV in a day. Okay, so 0 for the hours of TV is about over here, and there's no data below that. Okay. So let's just check out some z-scores and do some counts in the spreadsheet. So I've already made some calculations up here where I take the mean and I subtract the standard deviation, and then I take the mean and I add the standard deviation. So I'm just going to do that in a different spot over here. So I'm going to do using the 2 STD rule. I'm going to calculate the lower boundary for outliers and the upper. And it's pretty straightforward. You just take the mean, not the median. Why the mean? Because what is standard deviation? It's an average measure of spread from the mean. So we have to start with the mean, and then we can subtract, 2 times the standard deviation. I just click on them. Definitely don't retype them. That leads to errors. Equals the mean, click on it, minus, nope, in this case plus, because I'm upper, 2 times the standard deviation. Another spreadsheet tip: when we do math and we write a variable next to a number, we don't put the times symbol sometimes, and no symbol means times. A spreadsheet is a computer, and computers are only as smart as they were programmed to be. A spreadsheet needs to be told you should multiply, so I have to have that asterisk for times there. All right, so according to my calculations, the mean number of hours for BMCC students, at least my BMCC students in statistics, is a little over 3 hours per day watching TV type stuff. And the average spread is about 2 hours. And there's some rules about what percent of the population lives within 1, 2, 3 standard deviations from the mean. So we'll take a look at that here. Let's see, what do we got? 9, 28, 19, 6. Let's write that down over here. So this was 9, 28, 19, 6. That looks like 2 and 1. So these are the heights of the columns, the columns here. And if I wanted to see what percent of my students are within 1 standard deviation of the mean, I would count any student that watched 1 hour or more, but 5.5 hours or less, or sorry, 5.3 hours or less. That's not 5.5. So there's 28 in this group, and there's 19 in that group. So altogether, what does that give me? 47, and I had 65. So I could write, let's see, is that readable? I think so. 47 out of 65 students are within 1 standard deviation, I'm just going to call it an STD, of the mean. And then what is 47 out of 65 as a percent or a decimal? So that would be these 2 groups right here. So I want to add them up, parentheses, and then divide by the sum, or total, the count. And as a percentage, I get about 72% are within 1 standard deviation. Let's label that. And then similarly, we could go within 2 standard deviations, so that would be all of those 4 numbers right there. So let's add those up and divide by the counts. All right, so I got about 95% in there, so that is within 2 STDs, and let's do within 3 STDs just for fun. And I can't spell. There we go. So then we would want, so let's see, these 2 were within the 1st standard deviation, and then this is the 2nd standard deviation, so that would be the third standard deviation on each side, within, right, on each side. So let's add those up and divide by how many. And remember, if there's a number on a spreadsheet you need, do not retype it unless you have to, and usually you don't have to. Otherwise, that leads to errors. All right, so we get about 98% lives within 3 standard deviations. Who cares about that? Well, it turns out there's some general trends there. And if we look up our book, just for fun here, this is 2.7, is that right? Yeah, measures of spread. Let's blow this up a touch. So this section again defines more carefully than I have what standard deviation is. Hopefully you've read this and gone through the examples, and they talk about the idea of deviation, which is just how far is an individual from the mean, which leads to standard deviation. They talk about z-scores and some other fancy formulas, how to calculate it by hand, which we will never do. We'll always use the spreadsheet formula or some other tool. But down at the end, here we go. They give some general rules about most distributions. And again, distribution means the shape of the histogram of the data. And every data set's going to have a slightly different shape, but there are some kind of patterns that we see, like skewed left, skewed right, bell-shaped, U-shaped, bimodal, uniform, and there's many others. So one rule here is called Chevy's rule, and Chev had calculated that for most data sets ever, any data set, he was pretty bold there, 75% of the data should live, at least 75%, right? It could be more than that, within 2 standard deviations. Our data set here, we've got within 2, we got 95% within 2 standard deviations. Oops, where we go? Here we go. And then within 3 standard deviations, at least 98%. Now there's another rule called the empirical rule, and the empirical rule only applies to some shapes. Chevy's rule applies to any shaped histogram. But for ones that are bell-shaped and symmetric, and although mine has a little bit of a bell here, and again, different histograms, let's make another one just for fun. Every time you make a histogram, it's going to look slightly different depending on where you start and what the width of your columns are. So if you don't need a frequency table, which I don't really care about one right now, and you just want a histogram, Excel and Google Sheets will make a histogram if you just scroll down and ask for a histogram. So if you don't see it under suggested, then keep scrolling through till you see the histogram option. So this one doesn't look at all bell-shaped, but we have some control under Customize, and Excel does too. So what's it make choosing for a width here? It looks to be about 1.3-ish. What if we chose a width of 1 or 1.5 or 2? So I can kind of play around here with different widths. 2.2, right? Look at all the different shaped histograms we get. This is the same data, right? The same set of numbers. The graph looks drastically different depending on where I start and what my width is. Okay, 2.5 would not necessarily be a good one. Usually you want no less than 5 columns. You usually want 5 or more, 6 or more, and you don't want more than 20. So if I, in the histogram, tried to make the width like 0.1, that would be nonsense. That's a bad histogram. Even 0.5 is a bit too many columns for this data set because it's not a large data set. It's only 65 numbers. So let's go with 1.3 was what it started with, right? This doesn't really look symmetric or bell-shaped in most of the widths I chose for my bin width. And that's just how wide each of these columns are, right? 0 to 1.3, 1.3 to 2.6, and so on. Anyway, so I definitely meet Chevy's rule, and all data will. And again, Chevy's is at least. This is called the empirical rule, the second rule, and that says about 68% of the data, if it's bell-shaped and symmetric, should be within 1 standard deviation Chebyshev doesn't even mention one standard deviation because that varies too much between different types of distributions. And again, the distribution is just the shape of the histogram. 95%, according to the empirical rule, should be within 2 standard deviations. So although our data isn't bell-shaped in histogram, we pretty closely meet the empirical rule, 68, 95, 99 for 1, 2, and 3 standard deviations. All right, so let's go back and check that out here. All right, we have 72, 95, and 98 for 1, 2, and 3 standard deviations from the mean. Okay. All right, let's take a look at another data set. So counting by standard deviations. Are there outliers here? There is nothing lower than -1, right? Because you can't watch negative TV. But at least one person, there's a max of 10. Somebody said they watch 10 hours per day, and our upper rule for the standard deviation for outliers is 7.46. So if I were to sort this data, I could find other outliers. So we have 2 ways to find outliers, using the interquartile range or using the STD rule. All right, so here's a different sample. So I got a study that was done at a hospital or series of hospitals in Pennsylvania. And they gave me a couple of thousand birth weights of newborns over several years. And I took a random sample of those of 100 of them. So I have 100 birth weights and their gender here. And the average birth weight was 3,200 grams, which is 3.2 kilograms, which is what, like 6-7 pounds, somewhere in there, for a newborn baby. Now look at the distribution here. So here I have just a width of 500 starting at 0. So there were very few newborns that were born under 500 grams, very few between 1,000 and 1,500, very few 1,500 to 2,000. Most newborns are somewhere between 2,500 grams and 4,000 grams, so 2.5 kilograms to 4 kilograms. So there is a symmetric bell shape here if I ignore this tail. The tail is to the left, so we would say this graph is skewed left. The skew is to the tail. I regraph this by looking at standard deviations. So I put the mean in the center here, and then I subtracted the standard deviation 1, 2, 3 times to get those numbers, and then from the mean I added the standard deviation 1, 2, 3 times to get those numbers. And so these are the ranges of values that I'm looking at. So I'm choosing very special numbers here, the mean to kind of center at, and then the standard deviation to jump. And then I calculated, for example, these 2 columns, the 40 and the 37 here, that is within the first standard deviation of the mean. So remember, my mean is 3,200. That's going to be right in between these 2 columns. 3,200 is going to be in this column. So if a baby was exactly 3,200 grams, they'd be here, not there. That was 77 out of 100, or 77% of my data was within 1 standard deviation. 95% of my data was within 2 standard deviations, and 98 was within 3. Okay, so I have a slightly different version of the graph. Somewhere I lost it. There it is. This one right here. And I'm just going to make this a wee bit prettier. Actually, I don't need to. Let's just go back here. All right, next page. So here's that birth weight data. So just a reminder about a couple of things. We're counting by standard deviations, and so this number right here, I've graphed specifically my mean. Now sometimes when we make histograms, we don't get the mean as a specific number on that, so then we would have to draw it in, and so we'll do that in a minute just for fun. So that's the mean x bar. This number right here is 1 standard deviation to the right. So that to calculate that, I would take the mean and add 1 standard deviation. And this is x bar plus 2 standard deviations. Over here, I subtract, so this would be x bar minus 1 standard deviation, x bar minus 2 standard deviations, and last one is x bar minus 3 standard deviations. I didn't go 3 standard deviations to the right here because there were no babies that big. And we might ask, well, how come there's some really small babies, but there's not many really big babies? Okay, so think about that. There's probably a good reason. I calculated a whole bunch of summary statistics, coefficient of variation, which hopefully you're starting to get a handle on that. I'll talk more about that in another video. So from the STD rule, any baby that's born under 1,936 grams is unusually low in birth weight. Any baby born above 4,465 grams is an unusually heavy baby. And then we have another rule, the IQR rule down here, and it doesn't agree. They're not the same numbers. They're slightly different. It has a lower bound of 1,472 grams, so any baby under that weight would be considered unusually light. And any baby that has a birth weight of over 4,934 grams would be considered unusually heavy. All right, so the main idea here, I just wanted to get a feel for how we use standard deviation in statistics. That standard deviation is a measure of spread from the mean, and that we count that with z-scores, right? So the mean has a z-score of 0. So if I made an axis for z-scores, so instead of counting by birth weight up here, I counted by z-scores. 0 is the mean. That's 1 standard deviation and 2. So this, so the value. So if a baby was born based on this data set with a weight of exactly 4,464 grams, then we would say they have a z-score of 2, because average is 3,200. If a baby was born at exactly 3,200 grams, we would say they have a z-score of 0. So a z-score is just counting how many standard deviations a particular number is from average. And down here, the z-scores are -1, -2, and -3. So this is a number line based on z-scores. And above, this number line up here is just the birth weight in grams. All right, so each of these numbers on the number line, and these are all the same distance apart, and the distance I picked to make them spread out is exactly or pretty close to the standard deviation there. So you can scale by any number you want, whole numbers, decimals, anything. Okay, so that's it for now. Take care, do good math, see you in the near future. Bye-bye.